Interesting applications, particularly in what is called Arnold diffusion. And I will mention some problems which are still open. One of them is again under the name of Littlewood. And so that's the plan. So let me start with first. So first part is completely a description of the result in that we can call it result of differential topology or global analysis. So let me start with the following. We have a flow omega t sub t, and this will be typically, you should think of this as irrational rotation flow. That's where the results are. One would like to extend this to nil flows and more parabolic ones, but this is just a flow to begin with. Then you have a manifold, and this manifold will be real analytic. So what I'm going to say is not valid for, I don't know about C infinity, but analyticity is very important. And then you can think of this, like physics people, a forced oscillation problem. You have a differential equation. So you have vector fields F0, F1 up to Fm. These are vector fields on M which are analytic. And I'm looking at the system x prime equal to F0 x, which generates its own flow. This is like the unperturbed system. And now you have forced oscillations of this system given by, so you take some function, ui is a function from omega to r, I equal to 1 to m. So you have these m functions, and you take, so here's the picture, this is my omega, I have a trajectory here, point omega in omega, t sub t, omega is the position of omega after time t. And now you are taking time dependent perturbation of this vector field, so this is a scalar, and you multiply it by phi, I equal to 1 to m. So this is a forced oscillation problem where the differential equation has a very specific form, that you have an unperturbed vector field F0 and the perturbations come from other m vector fields. And one is interested in how the dynamics of the flow changes. And exactly in what way, I will explain you what are the questions one wants to look at. So that's a system. Now this system is of course parameterized by point omega in omega. So if omega has an invariant measure, you can think of this as a stochastic family of differential equations. And if you, let's make a blanket assumption that the solutions will exist for all t's. So you can always say the manifold is compact, or I don't want to assume manifold is compact, but you can always put some, so my hypothesis is, which I call hypothesis H, that is all solutions exist. All solutions exist meaning for all choices of initial conditions and for a suitable class of functions, say functions which are bounded. Suppose all solutions exist, then I write the solution psi, psi, initial condition x is in the manifold, and then omega is in your forcing. So the forcing is governed by a flow. So the dynamics will enter through the mixing properties of the flow. And this is the solution of this system. Let's call this star. Starting at, so the initial with psi at 0, omega x is x. So actually if you think of this as a mapping from omega comma t to psi x omega t, this is going to be, so if you think of this as a function of x, then this is a mapping from omega cross r to diffeomorphisms on m. This you think of as a mapping, x goes to this thing, and so this is a cocycle. So this is a nonlinear cocycle which are solutions of nonlinear differential equations. I will now consider a special case when the manifold is a Lie group and the vector fields are right invariant. So then your cocycle will be cocycle taking values into GL and R. I will be particularly interested in the so-called Schrödinger cocycle, which is a cocycle in SL2R. So the example that I want in, so this is a cocycle, and it will satisfy the usual cocycle identity, which says that psi of omega t plus s is same as psi of t sub t omega S composition psi of omega t. So, so we are talking about cocycles into infinite dimensional groups. So an example to keep in mind is when M is a Lie group G, and let's call the Lie algebra L of G, and now the vector fields are right invariant. So if I am given a function, let's call it A from omega to, and I take a subset S of the Lie algebra L. If I take a function, then I can look at the right invariant, the linear system as I call it. Thing like this. This is a cocycle into this generates a cocycle into a Lie group G. So this cocycle comes as a fundamental solution of a linear differential equation whose coefficients are given by A. A very special case which has been studied in the last 30 years is the case of Schrödinger cocycle, where where G is SL2R and the cocycle comes from the equation A. The equation, the matrix form is of this type 1, and there is a parameter lambda, so you can fix a lambda and you can think of this as a function of this form where Q is a function from omega to R. So cocycles which come from linear differential equations with matrix of this form are called Schrödinger cocycles, because when you are solving Schrödinger equation, it boils down to something like this at the end. Or you can think of this as a linear system which, if you write down the Stern-Liouville operator, which depends on omega, if you want to solve eigenvalue problem, this of acting on a function y equals lambda y, if you write this as a linear system, y prime is your x, then it boils down to that. Now, more than Schrödinger, my machinery will actually say more about Schrödinger with density. And that means instead of 1 here, you can have a function p. And these operators are also important. This can also be written as a differential operator. Instead of this, you can take d of p dt. So in any case, the point is, you have a subset S of a Lie algebra, let's only stick to SL2R, which can be very thin. For example, this subset is one-dimensional because the functions are taking values in subsets of the form. Let's ignore P for a minute. R is the only thing which is in your hand, lambda is fixed. So this is a one-dimensional subset in SL2R, which is three-dimensional. So we are looking at cocycles which are arising from very special kinds of differential equations. And the conclusions that I am going to make are the Lyapunov exponents of these cocycles in the smooth category have positive exponents. That's one of the conclusions. And some other things about Lyapunov exponents, and these are very recent results. Of course, Arthur Avila is one of the guys who produced these results of this nature. And I'll mention some of the things which are done in the last 2 years in this direction. And these results are of smooth ergodic theory, because these results are valid. The smoothness, degree of smoothness is very crucial. Some results are true in C1 but not in C2, and then C holder but not in C1, and so on and so forth. So this is the example which I want to focus on. So I have to keep an eye on there. I already exhausted 40 minutes. So how should I do this? So I will mention, I will make, okay. So I'll write 3 statements of 3 results. So first result, which will be about the general nonlinear thing. So in the general nonlinear thing, I will assume, so suppose, consider, so I will call this system star. Now of course, one has to assume something about the vector fields Fi. And so I will first of all state this theorem. So suppose, consider star, and you suppose H holds, meaning you assume that the solutions exist for all these. That's a minor hypothesis. Secondly, the family of vector fields F0 to Fm has SAP. So this I will tell you what it means. Strong accessibility property. So usually when you study vector fields and you want to go from on a manifold and you want to go from one point to the other along integral curves of these vector fields, there is a natural condition that the Lie algebra generated by this vector field. So you have a bunch of vector fields, you evaluate this at a point on the manifold that should span the entire tangent space. This is called Baroda condition. What we need here is this condition is not enough. You need a stronger condition. So I will formulate the condition that I mentioned is called AP. Accessibility property, that the Lie algebra generated by F0 to Fm. If you evaluate it at a point, so you get points on the tangent space, that should span the entire tangent space. I need stronger, so I will describe that later. But the conclusion is the following. So if this family has SAP, T be any positive number, then I look at the map. So I first of all, so let me describe the map I call Psi, which now I will call E. So this is a map from CR function. So what I will do is, here is my flow, here is some point omega. I take a flow box along this. So I will identify this with 0t. I will first take not even a flow box, let me just take a point omega. So I will think of this as the interval 0 to t. And so I take a function from 0 to t to Rm. So that means I am taking u1 up to um, that these functions. And then I evaluate, so the mapping is, this is mapped into, so this is a point here is u bar. This u bar is sent into psi of, what did I say there? This notation, I have to have a u bar here, and then we will put a t. So for a fixed omega, fixed x, fixed u bar, I have a solution. So I look at this mapping evaluated at t. This mapping as a mapping from the C infinity functions on an interval to the manifold M is a submersion, and this is uniform as x varies over a compact set K. So you are given a K in the manifold compact, and this is a submersion for all x's in K. So submersion means you have its derivative is onto. So if you take the derivative of this mapping and you identify the derivative of the linear space with itself, then it's a mapping from CR functions into the tangent space. And this mapping is onto means you can have a finite set of functions which when mapped by the derivative will span the entire tangent space. Always a little bit of differential geometry, you know, with a little bit of differential geometry, you know that any submersion theorem is very close to proving an open mapping theorem. And so from this submersion theorem, you can get an open mapping theorem, which I will first mention. And then I will tell you what this condition SAP is. SAP condition is satisfied by Schrodinger for example, if you look at this set of matrices, F has a P, point in the manifold, so you get vectors in the tangent space. This is, the span of this is the entire tangent space at x, and F has SAP at x if and only if span of L0 F x is the entire tangent space. So in particular, if you look at matrices of this form, I call this set S lambda, then S lambda minus S lambda. If you look at the ideal generated by this, then it's all of Sl to R. So even though this set S is one dimensional, it's big. These ideas of AP and SAP come from geometric control theory. And so I'll tell you what's the relevance of these ideas. So if you have a manifold and a bunch of vector fields, and you want to go from point, fix a point, and then you would like to go for a certain time t along the integral curves of the vector field. So you travel, so you chop t into t1 plus t2 plus tn, you operate by the first vector field for the first, so this, where you can reach is called a reachable set. So given a time t, the reachable set means all points you can reach along the integral curves coming from vector fields in the given set F. So if the vector fields have the property AP, that means if you look at all points to which you can reach in time less, so fix a t, capital T, and all times along which you can reach, collect all points which you can reach in time less than or equal to t, then that reachable set has non-empty interior. This follows from the Lie algebra condition. SAP is stronger. It says that if you look at all points which you can reach exactly in time t, then that set should contain an open, that set has non-empty interior. And this is very crucial difference. So the reachable set has non-empty interior, reachable set at time t is exactly SAP, and that plays a role. Now, having said this, let me give you the consequence of this, which has many other applications which I am going to explore in years to come. But this result, I think, is a very useful result in differential topology, which I will now mention. So, the open mapping theorem, of course, I can set it in more general terms, but for today, I will just mention this in the context of when the manifold is a Lie group and the vector fields are right invariant.
So can I ask you?
Yeah.
If the Lie group is simple, then this is where, I mean, the fact that it's simple is used to get this.
No. What do you mean? The simplicity of the Lie group doesn't enter so far. The fact that
the algebra is, what's the relation between the Lie algebra, the vector field Lie algebra, and the?
Here the Lie algebra is here the vector fields are right invariant. So here you identify the vector field by just a subset of SL2R, little SL2R. Yeah. So each point in here is identified with the vector field.
Does this become an ideal in SL2R?
No, it's not an ideal. So you look at this subset.
No, the ideal generated that you mentioned.
Yeah, you take the difference set and look at the ideal, then it is SL2R. That, in fact, interestingly, many examples, I am dealing with Schrödinger here, but there are many other examples in differential equations which are of interest in mathematical physics, like Rabi oscillators and so on. All of those examples somehow have SAP. By the way, these results are not true with just AP. So SAP, there are counter examples we have. So SAP is very important. So the stronger property is needed. And so not only we get the results for Schrödinger cycles, but for many others by this machinery. So open mapping theorem is the following. So now I look at, so again let me recall, you have a flow and I take a flow box. So this is your section sigma and a time t. So sigma t be a flow box. And now I have a function A from omega into subset S of the Lie algebra. Let's only stick to, say, little SL2R. This is true for general Lie groups. And then I look at the equation x prime equal to a t sub t omega x. Let's write down the cocycle at x sub a, which is a function from omega cross r to the Lie group. Now, what you do is you take this, so I now define a function psi, which is a function from CR functions from omega to S. So I'm looking at S valued functions, so that means I'm looking at differential equations of very specific form. You keep in mind the Schrödinger case. And what I do is you take, so this function psi associates with a coefficient function A. What you do is you take a cocycle and you restrict it. So this is a function I'm going to define by taking this solution and restrict it to the section sigma. So I get a function A going to x sub A restricted to sigma, and you evaluate this as at time t. So this is like a Poincare map. It's a Poincare map for the cocycle. So you take a cocycle generated by the differential equation, you restrict it to a section, and you evaluate it at a fixed time t. Open mapping theorem is the following. This mapping, which is taking a coefficient function A in CR omega S and throwing it into a CR function from sigma to the Lie group G. This mapping is open in CR topology. Though at those points A, those points are dense in CR topology. So I will say exactly what this means. And keep in mind, this is under the assumption that S has SAP. This means whatever phenomena that is happening for general solutions, you can realize it with solutions from differential equations which have a very restricted form given by this S-valued function. So let me write this statement and then maybe just mention how it, some few results about the economic exponents. So the theorem is S has SAP, then psi as a mapping from CR are greater than or equal to 2. That is needed because you have to interchange the derivatives in this proof. So CR omega S to CR sigma G. Sigma is the section, is open, is the set, so consider psi I should say, and then let me write it this way. Given A in CR omega S and epsilon positive, there exists an A1 in CR omega S and a delta. This delta will depend of course on A, epsilon and A1 such that the A1 has the following property, that if I take any function psi, which is psi is a bad choice, let's take phi, which is a CR function from the section to the Lie group, such that this function is closed within delta of the Poincare map for x1. That means you look at the cocycle for x1 restricted to sigma at t. This norm is less than delta. Any such function is realized as a Poincare map for another A2 which is close to A1. So then there exists A2 in CR omega S such that first norm of A2 minus A1 CR norm is less than epsilon, and the arbitrary function that we have chosen very close to the restriction of the cocycle to the section for coming from A1 is realized as the time one map for A2. So that means the cocycle for A2 sigma t is actually your function P of sigma for all sigmas in sigma. This is the mechanism by which once you prove a generic result in the class of all vector fields, then you can push it down to class of vector fields which come from special type. So for example, if you prove that all cocycles, CR cocycles which are SL2R value have certain property which is generic, then you can say that it's also generic when you restrict it to the class of cocycles which only come from Schrodinger equation. And this way, now so far small denominators have not appeared. And now I will mention a theorem which is only theorem I think I know of this kind, and then I will end. So there are various questions when you talk about cocycles in 2. So now let's take the general flow, forget about all of this, with an invariant measure, ergodic. And one can talk about differential equation. You take A from omega to S. S is in, say, let's only stick to SL2R, a little SL2R, and I'm looking at the cocycle which arises from this, X sub A, omega t. This will of course depend on the flow. And then you have various norms. The Lyapunov exponent, let me quickly define. Lyapunov exponent, lambda of A will be the largest Lyapunov exponent, limit of log norm x omega t, x sub A, 1 over t, this exists, and this is the largest Lyapunov exponent. Now, there is a general theorem which says that if your base flow is uniquely ergodic, then there are only 3 possibilities. Either the cocycle is uniformly hyperbolic, so theorem. I will not go into the definitions. UE is uniformly hyperbolic, means if you look at the bundle over omega, which is R2 bundle, then it splits as a direct sum of 2. One is contracting, one is expanding. These bundles are continuous. And in that case, the Lyapunov exponents are beta of A, beta and minus beta of A. Yes, there are only two. Then you have a situation which is beta A is positive, but it's not uniformly hyperbolic. So not uniformly hyperbolic. And the third possibility is all exponents are zero. Exponent zero case. In fact, there is a notion of Maher spectrum of a cocycle, and then I can formulate this in a better way. The spectrum is an interval, which is the analog of real parts of eigenvalues. The real parts, if your A is constant, then the analog of real parts of eigenvalues is exactly the notion of Maher spectrum, and there are three possibilities, which are these three, which I'm not going to go into. So there are the following questions. First of all, first question is, when is beta A positive? We are not going to worry about when is it positive. These questions actually you have earlier results. Some sufficiency conditions were given by Furstenberg. Several people have given this. My interest is in when can you say that the cocycles with positive exponents are dense in smooth category. So earlier results, original one was in 92 to Oliver Neal, which proves that this set, the set of cocycles when beta T is positive, this is dense in measurable category. First smooth result comes from work of Johnson, and then also more recently work of Krikorian, work of Vienna, Brazilian school. There are several such results about positive exponents. That's an easier problem. Second question, which I want to address because there is no smooth analog of this. Second question is, these two cases, when you have exponents either positive, when you have positive exponent, not positive, I mean uniformly hyperbolic. So let me call this sets of cocycles A for which exponent is positive, lambda A. That's one set one would like to understand. The other set one would like to understand is when XA is either uniformly hyperbolic or has zero exponents. So I'm going to say something about this. So it was a conjecture of Mahesh that any C1 surface diffeomorphism is generically either unsolved or it has all exponents zero. And the first step to prove this is to prove it in the linear case, which was done by Jairo Boschi in 2002, a student of Marcelo Viana. So we have to get some Brazilian people in here eventually, meaning Indian conferences, a very strong school in dynamics. So in 2002, Boschi proved that cocycles which have either zero exponents or are uniformly hyperbolic are dense in the smooth, in the continuous category. This result does not have smooth version. So after under 4 years, Boschi and Vienna proved Mahesh's conjecture, going from the linear result to the non-linear. And there they make an observation that this result is false in C1 when your underlying problem, they do it in a discrete case. I described continuous situation, but this result is not true in C1 category when the underlying automorphism is a total automorphism, hyperbolic total automorphism. This is false. And we have one result, joint work with Johnson, which was published last year. So about question 2, we proved that there is a Holder version of this result, and we can exactly see why it breaks down at C1. So I will mention this result, and then probably don't have much time. So theorem is the following. So here we need the base dynamics to be rotation by super Liouville numbers. So let's assume omega is 2 torus. It's actually work for more general things. Maybe for this proceedings I may want to do this, because this result can be pushed to not just for rotations. In this room there are a lot of parabolic experts, and my talk is very elliptic. By that I mean my underlying dynamical systems are rotations, and one would like to push these results to parabolic flows like nil flows. And that's a very interesting project. But anyway, first let me say that, and then I will say to which parabolic cases this can be pushed. In fact, I can say it now. Recently examples were constructed by Giovanni Forni and Corina Ulsigrai, right? Yeah. They have constructed certain time changes of time changes of Heisenberg, flows on Heisenberg group, right? Nil flows. Those are the examples where some of these techniques can be pushed. This I'm almost sure, but at least I can get one specific case of flow builds on Furstenberg transformation, x plus t, x plus alpha or x plus y. So you can have flow builds on this for which under suitable Diophantine approximation assumptions on alpha you can push these results. But let me just state it for irrational rotation. So dx is x plus alpha, and the rotation number has to satisfy a condition like this. This is less than some constant e to the minus, you want to have this to be qn to the 1 plus delta. If you have a decay like that, then you have a result. You can then say that cocycles which are either uniformly hyperbolic or have zero exponents are dense in Holder class of any Holder exponent, as long as it's less than 1. Then Q2 is dense. I'll just say that. That means this is dense in CR for any R between 0 and 1. And there is no smooth version of this. So it will be interesting to see if you can push smooth versions. Now, in the last 2 minutes, I will just mention some interesting and non-trivial questions. So proving positive exponent or density of positive exponents is much easier. I don't have much time to go into this. There are techniques of coming from work of Kotani and then techniques of rotation number which play a role in all of this. And then how does the first part of my talk fit into this? Those techniques give you results in the class of all cocycles. And my first part that I mentioned allowed you to push it for Schrödinger and other things. So that's the connection. But I want to just mention 2 more interesting questions. And the third question is rather hard. And that is, you are interested in looking at cocycles which are uniformly hyperbolic. That's in the first case. Density of this is a real non-trivial question. First of all, there is a topological obstruction. This set cannot be dense, and this has to do with homology of the space X. So for example, if X is simply connected, this set cannot be dense. This comes from an obstruction which is due to Moser and Johnson. By the way, this result is joint work with Russell Johnson. So there are obstructions. Last year, Avila, Boschi and Demanik, their paper appears in Duke Journal, prove a C0 version of this for rotations. Yeah, so we need rotations on the base. And I would like, one of my projects is to push that result into C alpha category. But probably is not true in C1. There is some work of Sinai and Dinabar which also hints at counterexamples in C1. So these results probably are not going to be true in C1. The other question, so the question is about proving uniformly hyperbolically dense in the smooth class is a non-trivial problem. And then even more difficult question, this is now in the context of Schrödinger. So you are only interested, so remember the cocycle coming from this particular matrix Q minus lambda 0. And now somehow the cocycle, if you look at the differential operator, there was this spectral parameter lambda. So the operator was some Laplacian plus Q equal to lambda something. This operator, the operator on L2R, has its own spectrum in terms of operator theory. And that's the spectrum of this operator is called one-dimensional Schrödinger operator. And there is a lot of work on the nature of the spectrum of the Schrödinger operator. And it was, the long-standing 100 years old results are when the potential is periodic or it dies down, it's in LP space, then the spectrum of this operator is just union of intervals. It was 1980 which generated this whole interest in this machinery when Moser first constructed a quasi-periodic Q for which the spectrum is a Cantor set. So now the spectrum of this differential operator can be very nasty for quasi-periodic Qs, which is exactly what we are dealing with. Our base flow is quasi-periodic. And so one is interested in cooking up Qs for which the spectrum is a Cantor set. And so such constructions so far are known due to Sinai and some examples, but they are always with elliptic base. Yeah? And there is a result of again Avila and Boschi, very recent. They prove that in C0 category for again irrational rotations, the nature of the spectrum is a Cantor set is generic in C0. And then there is an open problem. Can you find, so no examples are known where the spectrum is a Cantor set where the base flow has mixing. And so this is an open problem, and Avila has recently announced that he has found one example where the base is mixing and on which you can have Schrödinger operators to have Cantor spectrum. This is another interesting problem, and I think again there the examples constructed by Corina Ulsigrai and Giovanni Forni are going to be the natural candidates, because in those examples, if you understand and you understand this stuff, you will have, this is the machinery. So if you know enough, you can manipulate and produce, but I don't know. But that's an interesting problem, to produce mixing flows